The next objective is knowing when it's appropriate to use the normal approximation for a binomial distribution and to use it to solve probabilities. So a quick note about binomial distributions is they can be all different shapes and sizes. Here are two examples of binomial distributions that we've converted to histogram. If there are 5 trials and the probability of success is 0.51, you can see the distribution is roughly symmetric. If the probability of success increases, now it's 0.8, then we're going to have a higher number of outcomes. And so it looks more skewed to the left. So the shape depends on the number of trials and the probability of success. And binomial distributions can be all different shapes and sizes and have different centers and different spreads. But before we get to the normal approximation, there's one important thing I want to make a note about from binomial distributions. When we apply them to taking samples, then technically the independence trial or the independence condition is violated. And all samples that we take, they're done without replacement. So if you think about bins, I stands for the independence condition. And this is going to be violated if we're ever taking a sample. So to give you an illustration of that, let's think about if I had a class of, let's say I had 20 people in my class, and I wanted to take a sample of 3 people and ask whether they listen to Taylor Swift on a regular basis. So just for the sake of this scenario, let's assume that half my class of 20 listens to Taylor Swift on a regular basis. So think about the math of the probability of that happening, of me taking a sample of 3 people, and let's just say all 3 of them listen to Taylor Swift. So if I have a class of 20 and I know that half of them or 10 of them listen to Taylor Swift regularly, then the probability of the first person listening would be 10 out of 20, which is 50% chance. But once I've already selected that person, I don't put them back in the population, then there's only a 9 out of 19 remaining who listen to Taylor Swift on a regular basis, which means the probability is no longer 0.5, it's dropped to 0.47. Let's say the next person is also selected, then the third person there's only 8 remaining out of 18 total students. So the probability of success drastically decreases. But what we'll see is that if we start to have a larger population and a smaller proportion being selected, then the probability is only going to change slightly. So now let's bump this up. Let's say I want to take a sample from the whole school. So now let's say there are 2,500 people in the school, and let's look and see how much those probabilities change if we sample without replacement. If I expand this to the entire school of 2,500 people, then the probability that the first person, assuming that it's still a 50% chance, would be 1,250 out of the 2,500, and that's a 50% chance. But after I've selected that person, I don't replace them. Now there's only 1,249 left who listen to Taylor Swift regularly, and there are only 2,499 people left in the population. So now the probability is decreased, but it's a lot less of a decrease than before. Then for the third person, it decreases again, but it's still not as significant a decrease when the population size was only 20. Now I've increased it to 2,500. And so those trials are still not independent, but the probability change is so minor that it really it doesn't influence our final result that much. So now I want to expand it to think about the entire population of the US. There's over 3 million people in the population of the US, and think about how minor that change is going to be from the first person to the next person to the third person. If this denominator was 3 million and 150,000 on top, that decrease is going to be even smaller than this decrease here. So what I'm trying to tell you is that there's this condition called the 10% condition that says even though the trials aren't technically independent, the change in probability is so minor that it's safe to approximate them as independent. And so the 10% condition tells us that if we have a sample n that is less than 10% of the larger population, so capital N stands for the entire population, then it's safe to assume independence on these trials. this 10% condition is used to check and see if it's approximately independent. Next, we have an approximation for the shape of a distribution. One thing that's known about binomial distributions is as your sample size increases, the distribution starts to look more and more normal. So here the sample size is 10. You can see it's slightly skewed, but as we increase to 20, it looks roughly symmetric. And when we increase it to a size of 50, that looks almost perfectly symmetric. So we have this condition called the large counts condition that is used to check and see if we can approximate that the distribution is normal. The way we can check and see if the normal condition is met, all we have to do is calculate the number of trials or the sample size times the probability of a success. And if there are greater than or equal to 10 successes and there are greater than or equal to 10 failures, because this would be a number of trials times the probability of a failure, then it's okay to assume that the binomial distribution is approximately normal. So you can see, like I said earlier, it gets more and more normal as the sample size increases. And so there's no set number of the sample size. It's more about the relationship between the sample size and the probability of success. So as the number of successes, n times p, increases and the number of failures, n times 1 minus p, increases, the distribution becomes more and more normal. So what you really need to know from this page is that you use the 10% condition to check the independence condition when sampling without replacement. So whenever you're sampling without replacement, you need to check and make sure the 10% condition is met in order to calculate probabilities. Then you can check the large counts condition to determine if a binomial distribution is approximately normal. If it is normal, then we're no longer doing binomial calculations, then we're going to do normal calculations. So instead of binom CDF or PDF, we're going to do normal CDF or PDF. So let's look at an example. In a survey of 500 US teenagers aged 14 to 18, subjects were asked a variety of questions about personal finance. One question asked whether teens had a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. Let X equal the number of teens in a random sample of 500 who have a debit card. Explain why X can be modeled by a binomial distribution even though the sample was selected without replacement. So this without replacement is a key here, telling us that if we're sampling 500 people, then the probability of the first person having a credit card is 12%. But once that person is removed from the population, the probability of the next person being selected that has a debit card slightly changes. Is that change too much to calculate binomial calculations? And the way we check this is check the 10% condition. To check the 10% condition, we ask, is the sample of 500 less than 10% of the overall population? And the overall population is all US teenagers from 14 to 18. So it's safe to assume that 500 is going to be less than 10% of all of the population of teenagers. And the way you can show that mathematically is multiply 500 times 10, and that would give you what exactly 10% of the population would be. If 500 is 10% of the entire population of teenagers, that means there could only be, or there would be 5,000 teenagers aged 14 to 18 in the US. And it's obvious that there are much more than 5,000 teenagers in the US between these ages. It's safe to assume there are more than 5,000 US teenagers between the ages of 14 and 18, so the sample is less than 10% of the population, and that is why it can be modeled by a binomial distribution. So now let's use the binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. From the previous problem, we showed that X is approximately binomial. The number of trials is 500 in the sample, and the probability of success is 0.12. So all we want to do is find the probability of X being less than or equal to 50. Just like in the previous videos, we're going to write out the probability of X being less than or equal to 50, and we can use the calculator Since it's a less than or equal to statement, 50 will actually be the number that we put into our calculator, because remember, the calculator tells you everything equal to or less than whatever number you put here. So the net set number of trials is 500, probability of success is 0.12, and this gives us a probability of 0.0932, which means there is a 9.3% chance that we get 50 or fewer teens in our sample that have a debit card. Now, you might be wondering, why did you do binomial CDF instead of normal, like I said previously? Well, I haven't checked to see if the distribution is normal yet. That's what they're going to ask us in the next question, you can see. So I can't use normal CDF until I've checked the large counts condition. Before that, I have to use the binomial CDF function. So justify why X can be approximated by a normal distribution. Now I have to check the large counts condition. Large counts condition is simple. It's how many expected successes are there, n times p has to be greater than or equal to 10, and the expected number of failures has to be greater than or equal to 10. So if the probability of success is 0.12, that means the probability of failure is 0.88. So you can see there are 60 expected successes and 440 expected failures. Both of these are greater than or equal to 10, which means we can approximate this distribution, this binomial distribution, with a normal approximation. Now that we've checked the 10% condition and the large counts condition, we know that it's going to be normal, and we can do normal calculations. So they want us to use a normal distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. So it's the same question as before, but now, since we've checked and we can use a normal approximation, they want us to use the normal calculation and see how it compares with the binomial calculation. So first, we need to find the mean and the standard deviation of this normal distribution, or this binomial distribution. Just a reminder that the mean of a binomial distribution is n times p. The standard deviation is n times p times 1 minus p, the square root. So to find the mean, it's just the number of expected successes. 60 standard deviation, we plug in and get 7.266. So we want to know, with a normal distribution, the probability that it's less than or equal to, or I guess just less than 50 teens. So draw your normal distribution, shade your region, and use your normal calculations. This is the area that I'm trying to find. The mean is 60. Standard deviation is 7.266. So it's a normal distribution. So I'll use normal calculations now, and I'll write out my calculator statement here and see what the probability is. You should remember, for your normal calculations, you have to write out your lower. 0 is the smallest. It's the lowest number of people who could not have debit cards, right? Upper is 50. Mean is 60. Standard deviation is 7.266. Gives us a probability of 0.0844. So you can see it's not exactly the same as our binomial calculation, which gave us 0.0932. But it's an approximation. You can see that they're very similar, but not exactly the same. So you just have to remember, in order to do normal calculations, you have to make sure large counts condition is met, so you can use a normal approximation, and you have to make sure the 10% condition is met in order to assume that the trials are approximately independent.